So if we look into this second exercise, right here, this one I have already done. So this second slip circle, right, there are several things you need to look into before we start the calculation, right. One thing is we have two different soils here, right, because embankment sits on a different soil, right. So this one is this embankment soil has different properties, and the bedding soil have different properties, right. So here, for example, we have P value 20 and C value 20. Here P value is say 7 and C value is 75. So now the important thing is the shear surface. So if you look at this slip circle, you can see that this number 5, this slice 5 sits on soil number 1, or the embankment soil, right? Embankment soil. But if you look at the other 4 slices, 1, 2, 3 and 4, they are shear surface located in the soil beneath the embankment, right? So that means this part, right? So you have to apply them separately, right? Separately. So that's why when you calculate CR theta, you need to be able to calculate them separately. So here to take we have a different theta value. So it is 85, and this part is different theta value, that is 45. We don't need this 25. All we need is this 85 and 45. So two different slip surfaces. That is one thing. The other important thing is we can see that the angle, right? This we haven't encountered in the first one, right? If we look at the first example, this, the angles to the horizontal, right? You can see it is reducing, right? Starting from 4, 46, 32, 15, and then even though it is not clearly shown in this diagram, it is 0, right? But now if we look at here in the second diagram, if we start from slice 5, the angles are again reducing, 54, 29, 9, then it start to increase, right? You can see after 9 it is increasing. So most probably, and at the final one it is 30. So these angles actually not in this direction. We take this 54, that is in that direction, and we have 29. This should be 9. But these angles should be, because after 9 it is increasing. So this should be in the other direction, not in this direction, right? So this angle is 11 in the other direction, and this angle is 30. So why it is important? Because consider this is going to slide in this direction, and we know these slices have their own weights, right? Their weights, W1, W2, and also due to this there is a component in this direction, that is T. So T1 and T2. Now the sliding happens in this direction. These T1 and T2 are against that sliding. So this is actually act as a resisting force, right? These two slices. All these 3, 4 and 5 are for the direction of the slide, but this slices 1 and 2 against the slide, right? So therefore we have to assign a minus value for these two slices, because you know this T1, T is W sin alpha. If we take W and sin, we apply a minus value sin alpha. So we know minus sin alpha is minus alpha is minus sin alpha. Therefore we get something like this. But if you take the normal component W cos alpha, if we apply the same thing, we know cos minus alpha is same as cos alpha, so it doesn't change, right? But here it is. So the trigonometry actually works just fine for the slide, since we use negative values. So we have to be careful when we are looking at the diagram and also the table. We should identify that which are the negative angles. That is the important thing. So I'm going to use again an Excel sheet to show this. Now we know how to calculate W. Wait, I'm going to go through the same process again, just like in the previous example. Multiply everything by yield weight 19.3, so we get the values, and we know N is W cos alpha. This into cosines in radians, angle value, but remember now we have to make them negative. These are negative angles. Now you can see N doesn't change, all stays as positive because they are W cos alpha. But if you look at this, change the sign. Now so you can see the first two values are negative, then we have positive, and this is the summation of sigma t. But remember, when we calculate this sigma and tan phi, because now we have two different p's now. For slice number 5 we have this value, for all the other slices we have this value, so therefore we have to take them separately, right? We have to take them separately. So we have to find the sum only for this portion up to H7, only the first four slices. So this shows the sum up to the first four slices, and the other one is the lone one, 162, that is slice number 5. So when we apply this equation, tan phi values should be applied separately, right? Another thing is CR theta, they should be again applied separately. But sigma t, we know we get the sum, that is arithmetic sum. We get positive minus the negative, we get the summation of t forces in the direction of sliding. So let's calculate factor of safety now. So factor of safety we can write one is this CR theta. How to calculate CR theta? First theta value is 85 for these slices, and the C value is 75. You can see that the radius are the same. So the radius is not given here, so I'm going to assume a value, let's say 10 meters. Okay, 10 meters is the radius. So we have the same radius. So let's say for the first flow sizes, CR theta is we have cohesion value 75, see R is 10 and theta is 85, that is out of 120 plus. So the second part is slice number 5, this slip surface, that is from 45-degree angle and R is the same. So we have the cohesion value is in this soil is 20. So 20 into 10 into 45 by 180. So we have the cohesion part. Then we have to add the friction part. Again, these 4 slices with 7 and this slice with P value 20. So those 4 slices, the summation is 875. So we have 875 tan 7 plus the alone slice is this one, slice number 5, which is 162. This 162 and 20. So this you can see P value is tan 20, so that is tan 20. So we have both components, so this should be divided by the total summation of sigma t, that is 272. So by computing this, you will get the factor of safety, right? So now I think you have learned some aspects that you need to look into before you try to attempt and calculate the factor of safety of slip circles using the Swedish method of slices, right? So the next thing is, after this, the effective stress analysis, because up to now we have only considered total stress analysis, that means under saturation, or maybe just after construction, likewise, or maybe completely dry. But whenever you have a groundwater table, right, something like this, then we have to employ a different analysis, which is effective stress analysis, because we have the effect of pore pressure, right? So in the next lecture, let's discuss about how we analyze slopes using effective stress method.